Hi everyone, this is Chapter 20, Climate and Climate Change. First we'll discuss seasonality and climate zones on Earth. Second we'll discuss climate change definitions, controls, and how we measure climate change. And finally we'll discuss evidence for recent climate change and Earth's future in regards to climate. Your textbook introduces this chapter by discussing the Keeling curve, which is some data plotted on a graph of CO2 or carbon dioxide in parts per million versus year from 1960 to present. The Keeling curve is the record of measurements of CO2 taken on Mauna Loa in Hawaii, indicating that the concentration of atmospheric CO2 has been steadily increasing. Mauna Loa was chosen as the place to take these measurements because it is relatively far away from factories and large cities that could pollute and bias the measurements. This is representative as sort of an average atmospheric carbon dioxide measurement. The Keeling curve gives us an idea of scale for changes in atmospheric conditions, and also helps us start to think about the differences between weather and climate. Weather are atmospheric conditions at a given location and short period of time. So when you describe this week's weather or next week's weather or next month's weather, you're describing it for your location and a short period. Climate, on the other hand, is a description of atmospheric conditions for region or the entire Earth over longer periods of time. You're starting to thinking of decades to millennia and even to hundreds of thousands, millions, billions of years. When we think about climate, we can think of the entire Earth system. So these figures show average global temperatures in January and in July. In January, the northern and middle latitudes are cool and the southern and middle latitudes are warm, whereas in July, northern and middle latitudes are warm and southern and middle latitudes are cool, relatively speaking. This is a result of seasonality on Earth, which we'll discuss in the coming slides. Average global precipitation is also related to seasonality and shows a difference between summers and winters. January shows precipitation in centimeters on the top, and July precipitation in centimeters on the bottom. Looking back to some previous lectures, you'll notice that the El Niño Southern Oscillation has a lot to do with differences in precipitation in the Pacific Ocean and controlling global weather patterns. The Köppen-Geiger climate classification uses natural vegetation as the primary clue to the climate of a given area because plants depend on certain temperature and precipitation conditions to survive. So the KGCC groups different regions into A, B, C, D, and E, representing tropical, arid, temperate, cold, and polar regions, respectively. Each of these groups have subgroups or types and subtypes depending on certain temperature and precipitation conditions. Here is a map of the world with each landmass divided into one portion of the Köppen-Geiger system. So we see the 5 main climate groups represented here, A, B, C, and D, and E, and then subdivided groups by rainfall and temperature. You can see that some of the groups are much larger than others, and some are concentrated in only one area, and others are more well spread out. In order to understand different climate zones on Earth, different seasons, climate in general, we must understand atmospheric energy balance. This is the amount of energy arriving at Earth from the Sun, and if the balance is correct, we must equal the amount of energy emitted to space by the Earth. If less energy is emitted than arrives, then average temperatures at Earth's surface will increase, known as global warming. If more energy is emitted than arrives, then average temperatures at Earth's surface will decrease, known as global cooling. The figure below expresses some different components of the atmospheric energy balance. Some of these energy, incoming solar radiation from the sun, arrives to Earth's surface, gets reflected off. Some of it gets absorbed by clouds. Some of the atmosphere gets emitted to the surface. Then we get latent heat, conduction, and convection, quite a variety of conditions. If you take anything from this lecture, I would say that this is one of two most important slides. Understanding the connection between latitude and solar heating. Climate varies with latitude because the amount of solar energy absorbed at the surface varies with latitude. As the angle of incoming light changes from 90 degrees to a lower angle, light is more spread out, so the energy that an area receives decreases. So in the figure using flashlights, we can equate the 90-degree angle or intense beam to areas at or near the equator when the sun's light is concentrated in one location, whereas because of the angle of the Earth relative to the incoming radiation from the sun, non-equatorial regions, meaning the zones that are with increasing latitude, have light that is spread out over a larger area for any given period of time. Because that light is not as concentrated, those areas are not as hot on any given day of the year. The following two slides are just as consequential as the previous. These slides discuss how the seasons occur on Earth. And this is because the Earth's axis of rotation tilts at 23.5 degrees to a line perpendicular to the orbit around the Sun, and it maintains this tilted orientation as it orbits the Sun in one revolution every year. As a result, the amount of sunlight in areas away from the equator changes over the course of the year. This is shown in the figure below and will be shown in further detail in the next slide. However, it's important to point out in this slide a few different terminologies. First, as we move from winter to spring, we undergo an equinox. And as we go from summer to fall, we also undergo an equinox. These are the times when the night is equal on all parts of the globe. When we move from fall to winter and from spring to summer, we undergo the winter and summer solstices depending upon which hemisphere you're in. In the solstice, this is a period where you may receive the most or least amount of light in any given year. Listen to this part carefully, pause and repeat if necessary. At the northern hemisphere summer solstice, the North Pole receives 24 hours of sunlight, and northern mid-latitudes have long, warm days. So in the figure on the top left, you'll see that as Earth makes one turn or one revolution around in a given day of 24 hours, the North Pole is always receiving some sunlight and is not in the shadow, whereas the South Pole during this time never actually receives any sunlight and is always in the shadow, thus resulting in near or total sunlight in the northern hemisphere summer solstice at the North Pole, and then near or total darkness at the same time in the South Pole. The bottom figure shows the opposite occurrence. At the Northern Hemisphere winter solstice, which would be in December rather than June, the North Pole is dark all day, and mid-latitudes have short, cool days, whereas the South Pole receives complete 24-hour sunlight. This is the reason why we get different amounts of sunlight that change with the seasons on Earth. So now that we understand how sunlight, daily sunlight, and seasonal sunlight contribute to climate zones, we must also consider atmospheric and oceanic circulation. If you remember from previous lectures, Hadley cells, Walker circulation, and monsoons move moisture and heat in the tropics. Whereas at mid-latitudes, the circulation is slightly more complex, as large air masses move from the equator polewards and from polar locations towards the equator. Now that we have a good understanding of what climate is and how it's affected by different conditions on Earth, let's discuss climate change. Climate change is a set of conditions such as an overall increase in average temperature or overall change in precipitation that becomes the norm for a region. Global warming is an increase in average global atmospheric and sea surface temperatures, whereas global cooling describes a decrease in average global atmospheric and sea surface temperatures. The key here is that it's both atmospheric and sea surface temperatures that are changing. Given that paleo is a prefix meaning old, paleoclimate signifies the past climate for a region or globally. Indicators of past climate conditions include clues found in rocks, sediments, wood, ice, and other earth materials like fossils. Long-term changes in climate have occurred over millions to billions of years, whereas short-term changes in climate have occurred over decades to hundreds of thousands of years. Geologists study the stratigraphic record to track climate change over long-term or millions of billions of years. Although temperatures stay within a certain range, hot periods are known as hothouse periods and cold periods are known as icehouse periods. So the figure below shows the geologic time scale from the Archean to present, with changes in global temperature on the right, seeing it fluctuate. Important to note, as we move closer to the present in the record, there are more data to choose from and more data to collect in recent rocks, fossils, ice cores, other things. So our understanding of the record is much better the closer we get in time to the present. An example would be our understanding of the past 20 or 30 years of weather and climate is much more well established than our understanding of the past 20,000 years. We have satellite data, we have written records for the recent time periods, whereas we're relying on Earth materials and proxies for change in deep time. With that segue, short-term climate change is characterized by a variety of things, including historical records, microfossils and pollen, oxygen isotopic records, and ice or plankton, air bubbles in glacial ice, and growth rings on trees. Pollen in lake deposits changes as climate conditions change, and by studying cores of these sediments, we can determine a climate record. One great example of this is the difference in grass pollen versus spruce pollen in sediment cores through time. So at 12,000 BCE, in the picture on the right, we know that spruce forests extended as far south as the northern United States as a result of pollen and sediment cores, and we interpret this as indicating that the ice sheet was present just north of it and having cooler temperatures. Whereas today, the spruce forests exist only in much more northern latitudes, and grass pollen exists in the lake sediments in the southern latitudes, indicating a warmer climate. Oxygen isotope ratios in calcite that make up plankton shells in marine sediments provides an indication of past ocean surface temperatures. These ratios can also be measured from ice cores. I encourage you, if you don't understand how oxygen isotope ratios work, to look it up on Wikipedia for a detailed explanation of why a high level indicates a warmer climate and a low level indicates a colder climate. Finally, the spacing of tree rings records a history of temperature and precipitation during a tree's lifetime. So this would be a relatively short record of climate depending on the age of the tree. More growth happens in warm, wet years, producing wider growth rings than in cool, dry years. In the figure below, we have a stump showing tree rings, also a researcher extracting rings from a drill core that doesn't damage the tree. Air bubbles from ice sheet cores can give us information about atmospheric compositions. Other material trapped in the ice, as well as layering in the ice, provides climate information. In the case in the figure below, there's a temperature record for the past 800,000 years from an ice core extracted from the Antarctic ice sheet, with blue bars at the top indicating periods and duration of interglacial periods. In the current Holocene era, over the past few thousand years, there have been a number of warmer and cooler periods, with glacial advance and retreat. These periods are characterized by changes in temperature of several degrees Celsius. Now let us discuss long-term climate change controls. There are natural and anthropogenic controls. Natural long-term controls include solar energy output, because solar energy output changes over time as the sun ages. It becomes larger and hotter. Atmospheric composition. An atmosphere with the right amount of oxygen and carbon dioxide is necessary for life on Earth. It is varied over time, with carbon dioxide decreasing and oxygen increasing to current levels. Distribution of continents and volcanic arcs. Land at high latitudes leads to ice ages. Distribution of land areas affects the amount of rainfall and direction of ocean currents. So you can imagine, in addition, that if all continents are together in one supercontinent, the circulation of the ocean will be much different than is the case of the spread out continents in today's world. Sea level change is another long-term climate change control. With higher sea levels, this produces significant areas of continents that are covered with seawater, and the distribution of heat around the Earth changes, affecting climate. Volcanic activity also has an effect. Dramatic amounts of volcanic activity can increase CO2 and thus cause global warming. Finally, we have uplift of land surfaces. Uplift and erosion, which exposes rock, can lead to increased chemical weathering and absorption of carbon dioxide. Natural short-term climate controls include Milankovitch cycles, changes in ocean currents, large eruptions of volcanic aerosols, changes in surface albedo, and abrupt changes in greenhouse gas concentration. Note a mistake in one of the previous slides. I mentioned that there were anthropogenic long-term climate controls. This is not the case. All of these are natural. In 1920, Milutin Milankovitch recognized variations in the Earth's motions. There are three. Earth's axis undergoes precession or wobbling over a period of 26,000 years. The tilt of Earth's axis, which is known as obliquity, also changes over a period of 41,000 years. Third, the shape of the Earth's orbit, known as eccentricity, changes every 110,000 years. These motions combine to either increase or decrease the amount of sunlight and therefore the temperature at Earth's surface. The figure on the right shows the variations in precession, tilt, and eccentricity over the same time scale, with their periods being different. It shows them correlated with changes in average surface temperature of the atmosphere. Looking at short-term controls, we have volcanic aerosols. Volcanoes can add significant levels of aerosols into the atmosphere when they erupt. One example is Mount Pinatubo in the Philippines erupting in 1991, releasing high levels of aerosols that led to a decrease in global temperatures and precipitation over a 3-year period. The third part of the lecture will discuss evidence for recent climate change and a discussion of Earth's future. The evidence for recent climate change includes observed temperature change, observed sea level change, observed glacial retreat, change in the distribution of organisms, and changes in weather on global scales. Temperatures have varied over the recent past, shown in the figure on the left, but overall temperatures through the last century have increased dramatically compared to recent time. This is a result of the burning of greenhouse gas emissions and development of large-scale farming practices that support a global population in the past few hundred years. Warming has not been equal all over the globe. Between 1961 and 2014, more warming has occurred in the northern hemisphere than in the southern hemisphere, and land areas have been affected mostly in the Arctic, northern North America, and northern Asia. However, it can be seen from the picture that most of the world is warming, relatively speaking. Now let's turn to observed global sea level change. During the last glaciation, a huge volume of water froze into ice sheets, causing sea level to drop. When the glaciers melted, sea level rose by about 120 meters, or 400 feet. In the past few centuries, sea level has begun to rise again and is about 23 centimeters higher today than it was in 1885, shown by these figures below. Most glaciers have been shrinking over the past few decades, as shown in the picture of the Muir Glaciers, Alaska, which has retreated 12 kilometers or 7 miles between 1941 and 2004. This is shown in photographic evidence. Continental ice sheets have also been shrinking. Global glacial ice volume has been decreasing by 400 kilometers cubed, or about 100 cubic miles per year. One example is that ice mass loss in gigatons, as measured by the GRACE satellites in Greenland and Antarctica over the period of 2002 to 2012. Sometimes it's difficult or boring to try and interpret numbers on graphs, so your textbook shows pictures of maps of relative ice loss in Greenland and Antarctic ice sheets measured by the GRACE satellite for the past decade. As you can see, there is significant melting pretty much all of Greenland and in the West Antarctic ice sheet. We've also measured Arctic Ocean sea ice loss. In the Arctic, the ice floats over the oceans. Think of like icebergs. And the thickness of this ice has also decreased over the past 35 years. When we want to discuss the distribution of organisms, we can think of plant hardiness zones. And the figures below shows that boundaries between plant hardiness zones have shifted northward, where blue denotes shorter growing seasons and red indicates longer growing seasons. So the longer growing seasons are typified by warmer weather. As you can see, the blue areas are shrinking, warmer weather is creeping northward. And then we have global precipitation changes, which have been measured since 1900 to present. Decreases in precipitation are shown in green and blue, whereas increases in precipitation associated with warmer weather are shown in yellow to red. With this mountain of evidence, it's clear that there has been dramatic increased global change on Earth in the past 100 years, with increased sea ice loss, increased continental glacier melting, increased warmth and precipitation, and changes in the presence and location of organisms. Scientists are left to discern what causes these recent climate changes. So here we'll discuss natural versus anthropogenic, climate forcing or change. We'll discuss greenhouse gas concentrations, bubble composition in glacial ice, and isotopic compositions of atmospheric CO2, or carbon dioxide. In this slide, we go back to the Keeling curve, which shows increased atmospheric carbon dioxide from atop Mauna Loa since 1955. We've also been able to measure CH4 or methane and note that it is similarly increasing. So carbon dioxide and methane are increasing in recent time, but let's look a little further back. Studies of ice cores show carbon dioxide concentration varied between 180 and 300 parts per million over the past 800,000 years, the figure on the right. However, since the Industrial Revolution, the atmospheric carbon dioxide concentration has steadily increased to well above that level, to over 400 parts per million. This dramatic shift cannot be attributed to any natural event, but is instead contributed to anthropogenic change as a result of introducing greenhouse gases like carbon dioxide and methane into the atmosphere during the Industrial Revolution. As scientists race to understand how greenhouse gases affect global climate, they must first try to quantify the different natural and anthropogenic inputs known as sources of greenhouse gases into the atmosphere, and sinks, which are known as, or which can be described as the way that carbon dioxide is taken away. So natural sources include volcanoes, decay of organisms, animal respiration, and microbial respiration. Natural or anthropogenic rather, greenhouse gas inputs come from fossil fuel burning and decay of human-made things like landfills and agricultural things like livestock and rice. Sinks for natural sinks for greenhouse gases include dissolution in the ocean, weathering reactions with rocks and soils, incorporation by photosynthetic organisms, and chemical reactions in soils and atmosphere. How do we know that human or anthropogenic causes are to blame for these increased greenhouse gas emissions? Well, we can quantify how much greenhouse gases have been emitted and created as a result of the Industrial Revolution. These are shown in the figures below. In this case, on the figure on the right, we have higher or more sources than sinks, so we have excess source leading to greenhouse warming. Independent researchers, governments, and industries are attempting to model what Earth's climate will look like in the future. These models include interactions between atmospheres, oceans, and land over long periods of time. All reputable models, however, suggest significant warming continuing to 2100. As a result of this warming, temperate and desert climate belts will probably move to higher latitudes. So the distribution of vegetation on a warmer Earth will change. Because of warming, summers will become longer and the days with temperatures higher than 32 degrees Celsius are increasing. This is something we're measuring currently. Precipitation is projected to change as well, with winter precipitation increasing in the northern hemisphere and summer precipitation increasing in higher latitudes, but decreasing over the southern United States and western Eurasia. Models suggest current rises in sea level could increase by 20 to 60 centimeters by 2100. A sea level rise of 1 to 2 meters, more than this model suggests, would inundate areas occupied by 20% of the world's population. So an example would be the eastern coast of North Central America and the Caribbean on the right, were sea level to rise with active heights above sea level. Climate prediction is complex. There are things called positive feedback processes and negative feedback processes that affect model behavior. Positive feedbacks would include examples like water vapor increases that warm the air would lead to more water vapor evaporation, and so on. Or ice loss leads to more surface warming, creating more ice loss. A negative feedback process would be something like carbon dioxide increases, which leads to more plant growth, which allows for the reduction of carbon dioxide. Then there are uncertain feedback processes that we don't know about, like the overall effect of clouds. All in all, as the planet's surface continues to change as a result of human activity, we must be vigilant in trying to understand these processes and deal with them, as the lives of humans and biodiversity on the planet, our health, our systems of water, resources, and food all depend on it. As such, governments around and industries around the world have attempted to make global agreements to try and reduce and control future greenhouse gas emissions. Some notable examples of these agreements include the Kyoto Protocol of 1997 and the Paris Agreement of 2016, in which countries have made pledges to curb their greenhouse gas emissions. It remains to be seen whether these agreements will work and whether countries will adhere to their commitments. Finally, the last slide shows some suggestions for an approach to decreasing greenhouse gases that include reducing the waste of energy, developing more efficient vehicles, and switching to alternative fuels, collecting and treating carbon dioxide at large sources, which is known as carbon capture and sequestration, and personally, my opinion is the option of degrowth, to understand that we do not need to use as much energy to produce happy and healthy lives for ourselves, and governments and individuals must recognize that and must reward it.